We presented the concept of the inverse of a function in the previous video. In this video, we will use this concept to motivate the construction of the square root function. This will allow us to introduce the imaginary root I. The imaginary root will be important for understanding oscillatory dynamics in a future slide deck. In this discussion, we allow the function f to have the association rule f of x equals x squared. We ask, what association rule must function g have so that g of y equals the result of undoing squaring? We encounter a difficulty. Notice that, for example, -2 and +2 in domain x both correspond to the value 4 in codomain y. Thus, it is impossible to determine, given only the value 4 in domain y, whether to return the value -2 or +2 in codomain x. If we insist on defining our squaring function in the context of a domain that extends across both the entire positive and the entire negative portions of the number line, then the inverse of the squaring function does not exist. We illustrate this difficulty visually by reflecting the pink plot of f of x versus x across the dotted diagonal to obtain this purple curve. The purple curve is in many places double-valued, rather than providing one unique output as required for g of y to be a function. The object that we try to make look like a function by labeling the vertical axis g of y is, in fact, not a function. While the purple plot is itself not a function, it is possible to use this curve to obtain a plot that does correspond to a function, with the entire number line as its domain. We will construct this function, which is called the square root function, and which many people think of as a sort of inverse of squaring. To convert the double-valued plot into a single-valued plot, simply neglect the lower branch. The resulting object now has everywhere no more than a single value. Unfortunately, when evaluated at negative values of y, this plot has no value. This is not to say that the plot has a value of nothing or of 0, but instead that, at negative values of y, the plot does not have any value, not even the value 0. We will construct values for g of y to take when y is negative. We relabel the north-south axis the real part of g of y. We add an east-west axis labeled I times the imaginary part of g of y, with east pointing out of the page toward the viewer. The values on the east-west number line are multiples of the object I. The square with edges I and 1 touches at 2 corners, a new curve that is a rotated copy of the old curve we originally plotted in the vertical plane. This new curve lies in the horizontal plane. By defining I as the object that, when squared, returns -1, we ensure that the values of g of y represented by the complicated three-dimensional curve we have just constructed become, upon squaring, the heights traced out by the dotted diagonal line. The dotted line lies in the vertical plane. Thus, we regard the squaring function as undoing the square root function we have just constructed, here called g of y, this being the real part of g of y plus I times the imaginary part of g of y. In this slide deck, we illustrated how variables can be used to express quantitative relationships more concisely than can be accomplished by enumerating litanies of particular examples. Using variables allowed us to present the concept of a function, to present the concept of composing functions, and to present the concept of the inverse of a function. In this last video, we used the concept of the inverse of a function to develop the square root function, and we introduced the imaginary root I. In a future slide deck, the imaginary root I will be useful for describing oscillations in dynamic systems. We mentioned that functions are like sentences in mathematical reasoning, and the foundations in mathematical grammar we have begun to develop in this slide deck will provide a foundation for the mathematical language arts that we will perform in later tutorials.